get started. There we go. All right, chapter 3, section 5. Graphing f of x equals a times x minus p times x minus q. This, in short, is going to be known as intercept form. All right, so I'll refer to it as intercept form from here on out. But another way that you can refer to this, if you want to put this in your margins, another way we can refer to this would be also as factored form, to use a chapter 2 term. To kind of relate this form to what we've dealt with so far, first off, this is definitely a quadratic. This is a quadratic function, just like everything else here in chapter 3. And the real signature of a quadratic function is the highest degree of x squared, okay? And even though you don't see an individual x squared anywhere within this function, what you do see is something familiar to us from chapter 2. In chapter 2, we were given polynomials multiplied by polynomials. And if I were to go through the distribution and collection of like terms by multiplying these polynomials together, you'll notice that I would have an x times an x, thus giving me x squared. So if I were to go through the distribution process and collection of like terms in this function, I would get right back to x squared. And for the record, this is just a rearrangement of what we've seen before. In sections 1 through 3, we dealt with what's called standard form. Okay, and I'm about to describe 3 different forms of quadratic that we will have seen now. In sections 1 through 3, it was all this first form called standard form. Okay, and we spent 3 sections talking about it, but essentially it breaks down to a polynomial sentence, right? Ax squared plus bx plus c. Those are just polynomial sentences, right? And that's what we call standard form when it comes to quadratics. In section 4, which we covered at the end of last week, we learned about vertex form, where we had a parentheses, much like we see in this one here, but it was a single parentheses that was squared, right? And because it was squared, that's why it was still a quadratic, because I would end up with the next squared still. But we had a single parentheses squared, and it was in that form a times, in parentheses, x minus h quantities squared, and then it was a plus k outside of that. That was called vertex form. And in this one, we're learning about intercept form. And again, the signature look here will be that I have 2 parentheses that are multiplied by each other. Real quickly, I want to draw your attention to the fact that there is something similar that has been similar through each of these sections so far, and that's that I still have this leading term, a. A still does the same exact things that it did in sections 1 through 4. A determines the shape of my U shape, my parabola, the quadratic that will end up being graphed. A determines the shape of that U in 2 ways. The first way being steepness, which we've talked about several times over, how narrow or how wide that U shape is going to be. It depends on how large or small A is. And then the second way has to do with whether or not A is positive or negative. And positive will result in a happy face parabola, something that opens upward, or negative A would resort with a negative or a sad face U shape, something that opens downward, right? So A still affects the shape of this graph the same exact way. These 2 items are going to deal with the position of that U shape. And so here's how they're going to affect it. So there's a reason why we call it intercept form, just like in section 4, there was a reason why we called it vertex form. In section 4, vertex form gave us the vertex, most critical point of our U shape. Intercept form is going to give us the 2 other values, right? What we're going to learn is that these 2 parentheses are actually going to be able to give us what are called X-intercepts. Okay, so let me jump over to the whiteboard real quick to kind of show you what I mean, right? So on a coordinate grid, you have a y-axis and you have an x-axis, right? Now, when we dealt with linear functions way back in Math 1 or in middle school, right, you learned about y equals mx plus b. And that b represented a y-intercept. In other words, it told you where that line crossed this y-axis, right? And so when they talk about x-intercepts, now we're talking about where it crosses this horizontal x-axis. All right, so there are a couple of things that we're going to be really caring about. Now, one thing I also want to refer you back to is that when it comes to graphing a quadratic, a U shape, one thing mathematicians care about is, what's the minimum number of coordinate points I can get away with that still gives me the shape of my function without me having to do all this extra work of just plugging in some unknown amount of x values into my xy table. So let's say I had some U shape that did something like this, okay? Somewhere on a coordinate grid, whatever this may be, I have some parabola, some quadratic, some x squared version of a function, right? There's a couple things happening here, but again, from a mathematician's perspective, I'm going to really care about getting at least 3 points. And there's a reason why. Because in this U shape, there's definitely a critical point. It's what we call the vertex. In this case, because it's a happy face, it's going to be this bottom or minimum of my U shape, right? The vertex being the critical point, the interesting point, the change in direction or change in value of my U shape, right? So if it was a happy face U, it's what we call a minimum. If it was a sad face U and opened down the opposite way, then it'd be the maximum. But in either case, the vertex is pretty easily identified if I'm just looking at the shape. So if I can identify the vertex, like in section 4, I have the most critical point of this parabola, but that's definitely not enough information to graph the whole thing, because there are lots of things that can go through this point in lots of different ways, right? Whether or not I know it's the vertex. So I need more than 1 point. And what we learn is that this is a symmetrical shape. Basically, everything on one side of this U shape will be perfectly reflected over to the other side. Forgiving my sketched drawing here, but in reality, if I were to graph an actual parabola, right, something a little bit more accurate than this, everything on one side of this U shape will be perfectly reflected the other, and it's going to be split by what we call an axis of symmetry, right? And we learned about this in section 1. In section 1, we learned about this axis of symmetry that basically chops this U shape in half. Okay, and we can treat it kind of like a mirror, where that any point on one side of this U shape is perfectly reflected over that mirror to the other side. That makes this axis of symmetry a very critical aspect of a parabola. And also notice that it goes directly through my most critical point, being the vertex, because the vertex would be the point that's on the mirror. Even just a fraction of one side would be perfectly reflected to the other. There's nowhere to reflect when you're on the mirror. Okay, and so what I'm going to care about if I'm graphing a parabola is I do want to know where my vertex is, and then I want to pick a point on either side. And the reason I want to pick a point on either side is because I want to represent one side of this U. If I pick both points on this side, I definitely get one part of a curve, but I have no idea what's happening over here. Okay, I'd have to reflect something to the other side so I can get the true U shape going on here. So I want points on either side. And what we're going to discover in this section is that the x-intercepts, the points along this x-axis that this parabola is going to intercept, will also form the 2 points that we want, and they're going to be symmetrical to each other. In other words, they're going to be perfectly reflected over. And again, my drawing's a little inaccurate here, but again, what we'll find is that a point is perfectly reflected over to the other side. And so what we're actually going to start with in this section is being able to identify these 2 points. And if I can identify these 2 points, I can figure out what chops them exactly in half, namely the axis of symmetry. And using the axis of symmetry, I can locate where my vertex is. That's essentially going to be the strategy in this section, that we'll be able to identify these x-intercepts. And from that, we're going to figure out what chops them exactly in half. Using that axis of symmetry, that x value, we'll plug it back in to find our exact location of the vertex. All right, so let's see this in action. All right, so back to our notes very quickly. All right, so again, these 2 parentheses are going to give us what are called x-intercepts for a simple reason. When it comes to an x-intercept, some point that's on the x-axis, that means that the y value in both those coordinate points is going to be 0. Why is that? Because if I imagine my x-axis, and if y is 0, that means it goes up 0 and it goes down 0. So it's stuck on the x-axis. That's why these kinds of coordinate points are called x-intercepts. All right, so how do we go about finding out what's exactly in the middle that's going to chop it in half? we're going to revisit a formula that you actually learned in Math 1 or before, and that's the midpoint formula. The midpoint formula, also known as just taking the average, right? So basically, I have these two unknown values, whatever they may be, P and Q. And if I want to find out what's exactly between those numbers, here's the process I can go through. Add them together, divide by 2. Okay. Some of us would attempt to like draw them on a number line, maybe use an actual visual graph or coordinate grid to find out, like just count squares or whatever to find the exact midpoint. But mathematically, one thing we can always do is this: taking an average or finding the midpoint. By finding out what's exactly in the middle of this, I'll be able to identify this result being the axis of symmetry, because it's going to be symmetrical. It's going to chop it in half. And we'll use that value to plug back into whatever formula we were originally given to locate the coordinate point for the vertex. So let's see this in action. We're going to do this one example and be done for today, right? So this will obviously be in what's called intercept form or factored form, because I'm going to have these multiple parentheses and stuff. So let's go ahead and jump to the whiteboard to see how this is worked out. So again, what will you see? You're going to see some given function, in this case, a times x minus p and then x minus q. But in this example, we have x plus 1 and then x minus 5, right? So again, for the record, if I were to distribute and collect these like terms, I could get this to look a lot like something that we've seen in sections 1 through 3, ax squared plus bx plus c type of form. But we're going to use this form. And I'm going to first show you the shortcut way to solve your x-intercepts here. And the shortcut way is simply to do this. Take the opposite sign of whatever you see here. Okay, so for instance, I have a positive 1 here. My opposite sign is going to be a negative 1. Negative 1 will be one of my x-intercepts. Over here, I have a negative 5. The opposite of that would be a positive 5. So negative 1, positive 5 will end up being my x-intercepts. That's the shortcut way to do it. Let me show you the slightly longer way, and by slightly longer, it's only ever so slightly longer. You can take either of these parentheses and set them equal to 0. We're going to use a concept here that we've dealt with before, the zero product property. Basically, parentheses number 1 is x plus 1. If I were to set that equal to 0, what I'm essentially doing is I'm saying, like, all right, when will y equal 0? Right? If y equals 0, again, from a coordinate perspective, from a visual perspective, that means that from a y vertical place, I'm not going up any and I'm not going down any. So that's why I'm going to care about setting it equal to 0. And why specifically just this parentheses? Because if just this parentheses equals 0, then it doesn't matter what this guy ends up being. 0 times that thing will end up making the whole thing 0, thus giving me an x-intercept. It's a really quick solution here, not terribly long. If I want to get x by itself here, I would subtract 1 to both sides, and I'd get x equals the negative 1 that we identified at the beginning. Okay. Again, the fast way would just be to take the opposite sign here. More precisely, I take the whole parentheses, set it equal to 0 to tell me that x equals negative 1 will be one of my zeros, one of my x-intercepts. Okay, you'll see both terms used interchangeably. So again, the logic here is if I were to take this x equals negative 1 and plug it back in, negative 1 plus 1, that officially goes to 0. And it doesn't matter that this will go to negative 6. 0 times the whole thing would result in a y coordinate of 0. Basically, I've created a coordinate point, negative 1, 0. I can do the same thing for the other parentheses. Again, this will be familiar to things that we did in chapter 2, but set the other parentheses equal to 0. Again, now if this parentheses equals 0, it doesn't matter what this guy turns out to be, because 0 times that will make the result 0. And again, another quick solution. But here I would add 5 to both sides, and I would get x equals that positive 5 that I mentioned before. Again, the opposite sign here. And again, what we have created are two coordinate points, negative 1, 0, 5, 0. Those end up being x-intercepts. And so if you're keeping score here, if I were to, say, do an xy table, right, x, f of x, or xy, right, and if I want to graph a parabola, I need 3 points, right? I need the vertex, and then I need 2 other points, 1 on each side. We have just found the one on each side, being negative 1, right, If I were to plug that -1 back into the formula, again, that first parentheses would go to 0, and then it doesn't matter what the rest is because my point becomes -1, 0. The same thing will happen when I plug in 5 for the other parentheses. So when I plug in 5, it spits out 0 as well. So I basically have created 2 coordinate points to plot in a coordinate grid. The piece that I would need would be something in the middle, but not just some random something, because so far this is just representing each side of the legs of my U shape. Right? So to kind of show you visually what that would look like, here is the page from the solutions, again, uploaded to Google Classroom. All right, so just to show you graphically what's happening here, right? Each of these 2 points represent those 2 zeros, those 2 x-intercepts that we just identified. This one's -1, 0, left 1, up and down 0, thus on the x-axis, thus an x-intercept. This one's the 5, 0, to the right 5, up and down 0. So these 2 would be the x-intercepts, also called the zeros of the function, where it crosses the x-axis. Now, there are lots of different parabolas, lots of different U-shapes that can pass through these 2 points. It's not just the one that we're going to end up graphing. So I need more information. I need that middle point, that middle value in my XY table, also known as the vertex, the most critical point of the U-shape. And again, the logic is that when I know I'm dealing with this symmetrical U-shape, I know I can chop it directly in half and locate my vertex. This chopping in half is also known as the axis of symmetry. Okay, and so here's where we're going to use the concept like, well, I can pick some random value in between that just gives me some random other coordinate point, but I want the most critical one, the one that's exactly in the middle, because that exact middle will represent the axis of symmetry and the vertex. So I'm going to use this -1 and 5 to figure out what value is right here. Now, graphically, I could just look at the coordinate grid and hope to count squares and get a nice convenient value, or I could use this midpoint formula. Basically, add 2 items together, divide it by 2. What are these 2 items going to be? They're going to be the -1 and the 5. This is another way of saying find the average value between these 2 values, or another way is find the midpoint between those 2 values. So if I were to add -1 and 5 together, I would get +4. Don't lose track of those negative signs, right? I get +4 over 2. And when I reduce 4 over 2, I end up with this 2. What's the significance of that 2? That 2 will represent my axis of symmetry, but more importantly, I can use that 2 to plug back into my XY table to find out what my vertex is going to be. Because again, the vertex has to be on top of the axis of symmetry. And when I plug 2 back into my original equation, let's see what happens. Let me scroll down a little bit further now. So my original equation was this. It was y equals -x plus 1. But instead of the x, I'm going to be plugging in that 2 value. And then it was x minus 5. Again, I'm going to replace that x with that 2 value. And so when I plug the 2 in, this is, again, just what we would do for any xy table. What I'm going to end up with, deal with your parentheses first, right? 2 plus 1 is going to give me a +3. And then the 2 minus 5 is going to give me a -3. Okay. And so in this case, now I just have string multiplication. So I just have to multiply each of these items together. Technically a -1 times 3 is -3. That -3 times a -3 is going to give me 9. All right, well, what's the significance of that 9? What does that 9 mean? What we've just created is a coordinate point. When I plug in x equals 2, and I plug it back into the original equation, it spits out this +9 result. We've created a coordinate point, and more importantly, we found the y portion to my vertex. So when 2 was plugged in, 9 popped out the other side. All right, well, visually, what would that look like? Okay, so here's that graph again from our solutions, right? Again, our 2 x-intercepts in this intercept form, or this -1, 0 and +5, 0, by first doing this average piece right here to find this +2, what we found was that at +2, or to the right 2, this point right here is exactly in the middle between the -1 and the +5. And if I were to do a line through that +2, I create an axis of symmetry. And when we plug the 2 back into the original equation, we're looking for basically where along that axis of symmetry is my coordinate point, my vertex. And we found it to be up top. And when we plug 2 in, we got +9. So when I do +2, or to the right 2, up 9, there's my vertex. And it makes sense that when I connect these dots with that U shape, right, my 2 X-intercepts and my vertex, it makes sense that it's a sad face, actually. Because if I look back at the original equation, you'll notice that A out here in front is this negative sign. Now, technically, there is a number here. That number just happens to be 1. So a -1, that negative sign for us is going to mean sad face. So my result, my graph of this sad face U does make sense. It's like a nice little quick sanity check for you. But that's how we're going to go about graphing these intercept forms. We get 2 free coordinate points, but then we use those coordinate points to figure out where the axis of symmetry is, and in turn, where the vertex is. All right, let me go ahead and stop recording.